Okay, I think we can begin. So today we have a bit of an unusual seminar, as you can see from the setup on the table. I will first ask Paweł Nurowski to introduce our guest today.
Hello, it is my pleasure to welcome here Professor Lane Hughston from Goldsmiths College of University of London. I should say a few words about Lane. Lane Hughston is he graduated at the University of Oxford under supervision of Roger Penrose, and from there he had a very broad and very successful career. So he's a man of infinitely many talents. He actively now works in mathematical physics, in mathematical finance, and in mathematical theory of music. There are much more talents of Lane, who is erudite. I spoke with him, and every moment he gives me new information about some other subject. Lane also happened to be, for about 10 years, the head of all mathematicians in Merrill Lynch, which is just one of the biggest investment banks in the universe. So I am very happy that Lane is here, and that will tell us something about music.
Well, thank you, Paweł. It's a great pleasure to have the opportunity to be here in Warsaw. I'm going to talk about configurations, tessellations, and tone networks. I think you all know what a tessellation is. By a configuration, I mean a kind of a geometry made out of points and lines on the Euclidean plane. So if we have a collection of points and a collection of lines that meet in a certain way, then we call that a configuration. And there are many examples of configurations. I'll come back to that in a moment. And it turns out they have something to do with music, which is basically the topic of this talk. Now, the idea of a tone network is rather special. It originates with Euler, the mathematician, who in his very first book, which was actually on a mathematical theory of music, invents this thing called the tone network, or he called it the tonnetz. And tonnetz has now, the German word has now been adopted into English to refer to tone networks, so I'll call it the tonnetz, and plural tonnetz. So the tone network is a kind of network of chords. So Euler found a way of linking major and minor chords together to give a network. And you can use his network and its extensions and various modifications thereof as a basis for analysis of music and composition of new music. So the work that I've been doing this is in collaboration with Jeffrey Boland, who's based in California. So the tonnetz associates major chords and minor chords. So basically 3 minor chords are associated with each major chord, and 3 major chords are associated with each minor chords. And this is done according to a special arrangement. So I think you all know what major and minor chords are. So that is a major chord, that's C major, and that's the corresponding minor chord. We call that the relative minor, C minor. Major chords are usually associated with positive emotions, happiness, and so forth, and minor chords are usually associated with somber emotions, or possibly sad, or even funereal type emotions. And if you take a major chord, then you can modify it by adjusting one tone to get a minor chord. So for example, if you take this C major chord and then you lower the C to a B, you get that chord. That's a B, an E minor chord. So there's E minor. This is called an inversion of E minor. So the transition from C major to E minor is like that. But there's also a transition from C major to C minor, which we discussed a moment ago. And then if you consider all the possibilities, there's one more. You can raise the G to an A, and you get this chord. That's an A minor chord. We normally hear it like that, but this is one of the inversions where you put the A on the top. So in summary, you can start with the C major and get C minor, or you can start with the C major and get E minor, or you can start with the C major and get A minor. So those are the three minor chords that are associated with the C major chord. But at the same time, you can start with a minor chord like C minor. So we can take the C minor and then we can lower the bottom note and get this rather pleasant E flat major chord. So that's going from minor to major. Alternatively, we can raise the last note and get an A flat, so that's another major chord, A flat major. And then finally, we can lift up the middle note from the E flat to a C, and we get back to the original C major chord. So in summary, we have the transition to C minor, and we have the from C major to C minor, we have C major to E minor, and C major to A minor. But we also have C minor to E flat major, and C minor to A flat major, and C minor to C major. They're changed by one note. So you can ask, mathematically you can say, if I start with a major chord and change exactly one note, can I get a minor chord? And there's exactly, given any note of the major chord, there's exactly one way to change it to get a minor chord. So that's why there are three different ways of getting a minor chord from a major chord. And the same is true of minor chords. And the new chords are very close to the original chord. I mean, in other words, the change, it isn't a big leap, to some other part of the keyboard. It's just one semitone or one tone away on one note to get from the major chord to the minor chord. And this has played a role in a lot of people's thinking about this relationship. So you can start with any chord like D major or E major, F major, and so on and so forth, and then construct the 6 chords connected with, say, F major and F minor. And gradually you link them all together and you get a network. And that is the Eulerian tonnetz. So we can draw a picture of it. The thing is that the tonnetz was, after Euler's investigation, it lay dormant for a long time, and then there was a man called Oettingen, and then later Hugo Riemann, particularly, no relation to the famous mathematician, had a major sort of redevelopment of the tonnetz in late 19th century and early 20th century, where he rethought many aspects of the tonnetz, and then it lay dormant again right up until the 1980s. And then at that point, a man called David Lewin, his name is mentioned there, and his circle of students and colleagues started developing the tonnetz again. Lewin was the first one to bring group theory systematically into music. And in this respect, the musicians were sort of 50 years behind the physicists in recognizing, group theory as an important force in their way of doing things. But it eventually entered into the subject and has sort of changed it forever as a consequence. So if you think of music and mathematics, having to do with frequencies and acoustics and all that sort of thing, well, that of course is still important, but the musicians have moved on to higher mathematics in their thinking, and the results are actually quite interesting. So I've explained how the C major and C minor can be brought into each into 3 different forms of the opposite mode. When you link them together, then you get a network. So this is the tonnetz as it's often represented. So it takes a moment to get the hang of this and start navigating your way around. But I'm using a capital M to denote major and a small m to denote minor. So that CM, where the mouse is located there, that's the C major chord. And the major chords are denoted with a white vertex and the minor chords with a black vertex. And you'll see that this C major sitting here is connected to C minor and to E minor and to A minor. So those are, of course, the three chords that we were discussing earlier when the E minor and the C minor and the A minor. And then if we look at the C minor chord, we'll find that it's, which is up here, you'll see that it's connected to the A flat major, E flat major, and C major. So that's the little part of the tonnetz that we worked out in detail at the piano a few minutes ago. But then it extends on and on and on, and eventually you cover all 24 of the major and minor chords. And curiously enough, the graph starts repeating. So it's a tessellation, but it's a periodic tiling. And so you can see some chords down at the bottom that, like this D sharp, which then links up to the E flat up here. So you can make identifications at either boundary and close it up, and it has the topology of a torus. So all of that was recognized in the 1980s, and that is the mathematical object, which is the tonnetz that is a kind of center of attraction of a lot of work. So what I would like to talk about here is a kind of another way of viewing the tonnetz, which I think is quite efficient. It's a graph-theoretic way of looking at it. So rather than a tessellation, we're going to construct a so-called Levi graph. So this Levi lived in the 20th century. He gave lectures on graph theory, and he put forward this notion of what now is called a Levi graph. So a Levi graph is a graph that's bipartite. That means it has two different types of vertices, which we can call black and white. And the white vertices are only connected to black vertices, and the black vertices are only connected to a white vertices, but a white can't connect to a white, and a black can't connect to a black. So that's rather like our major and minor chords in the tonnetz. For a Levi graph, the girth of the graph has to be greater than or equal to 6. So by girth, I mean the minimal length of a cycle within a graph. So by a cycle, I mean a set of vertices that are linked around in a kind of a circle and eventually come back to the place that you started. So what we find is a graph with 36 edges. So this is another picture of the tonnetz. This particular picture was actually discovered quite independently of the musicians by a British mathematician called Cohn-Waller, and he was a combinatorialist and a category theorist, and he wrote an article on group theory and music, which he published in the Mathematical Gazette in 1978, and he has exactly this picture in it, and he discusses the group of the graph. But you'll see that this graph is the same tonnetz that we've been discussing. So there at the top, you'll see the C major. And if you follow the three edges, it's connecting to C minor down there. And then on either side of it, you'll see the E minor and the A minor. So that's the first connection. And then if we look down here at the C minor, you'll see it's connected to the E flat major and the A flat major, and then back to the C major. So those are the three chords connecting to the C minor. And you can tell from the overall symmetry of the graph that it respects the kind of natural geometry of the chromatic scale. If we were to kind of rotate cyclically the chromatic scale through all of its 12 notes, then that corresponds to a kind of action, on the graph itself, and this reflects basically the structure of chromatic music, which was what we had from more or less the second half of the 17th century, on into the present. So the curious thing about the tonnetz is that it allows you to identify many cycles. So I like to use the Levi graph as a way of looking at the tonnetz so you can see cycles. So a good example of a cycle is starting at C major, you can come down to C minor and then go to A flat major and then over to G sharp minor, up to E major, then up to E minor, and then back to C major. So that is an example of a hexacycle. It's a collection of 6 chords that follow in succession, by the pattern that I described. I'll play that particular hexachord. So we start off with C major, and then go to C minor, and then up to A flat major, and A flat minor, or equivalently G sharp minor, and then E sharp major, E minor, and then back to C major again. So that is an example of a hexachord. It enters into music, and you find these hexachords in the music of Schubert, in the music of Chopin. You find it in Beethoven, all the great composers of the 19th century, and yet you won't find it in any of the classic musical texts. So they were, as it were, unconsciously using the cycles of the tonnetz in their compositions. When you set it up orchestrally, then it begins to be impressive. Here's the same hexachord, but played electronically on some brass instruments that we've manufactured. We'll play it twice. So that's C major, and then C minor, A flat major, G sharp minor, E major, E minor, and then C major again. So that's an example of a hexacycle. So you might wonder, what is the structure of the hexacycles in the tonnetz? And so you can see that there's one up there starting at the E minor and the C major, but there's another one starting at F major and A minor, and yet another one starting at B flat major and D minor, and finally a fourth one starting at E flat major and G minor. So the 24 chords of the musical system are divided into 4 disjoint subgraphs. So those are called the 4 hexatonic sequences, hexatonic hexachords, and they sort of provide a kind of organizational principle for many compositions. But they aren't the only hexacycles. You can identify other hexacycles that are there in the graph. Here's another one that's kind of less obvious. You can start at F major, move to D minor, B flat major, and then you cross over at this point to B flat minor, up to D flat major, then to F minor, and then back up again to F major again. So that gives you a second class of hexacycles. And in fact, there are 4 of the first category of hexacycle, but there are 12 of the second category of the hexacycle. I'll play you what one of the second category hexacycles sounds like, so you get a feeling for it. Starts the same, of course, but it changes. We'll play it one more time. So you'll begin to hear sounds that are reminiscent of things that you've heard before within this, but in fragments. It'd be unusual for a composer just to repeat the whole cycle. That'd be they like to break things off. So, for example, Beethoven, in his Ninth Symphony in the Scherzo, he has a cycle where he runs almost all the way around the perimeter of the tonnetz. The tonnetz has 19 chords in it. There's one point where, in a moment of madness in the Scherzo of the Ninth Symphony, he, in rapid succession, does 19 chords, all different from one another, running around the whole of the cycle of the tonnetz. And then, in the manner of art, at some point he sort of gets tired or gets distracted and then suddenly stops and wanders off in another direction. So that's sort of typical of what happens. The composers will get started on a cycle, but maybe it's a matter of good taste. They think that they should, break it off. Maybe they want to leave you wanting more, rather than leaving you thinking that you've had enough. Well, there are other cycles as well that are quite interesting. I'll show you the octacycles. So if we start at this C major, for example, then if we move to A minor, then cross over to A major, up to F sharp minor, then down to G flat major, over to E flat minor, up to E flat major, down to C minor, and then back to C major. That encompasses 8 different chords. And you see there's a little twist at each corner, so it looks like a kind of a hat, a sort of a 4-cornered hat. And then by inspection of the graph, you'll see that there are exactly 3 of these octacycles. Here's the sound of one of the octacycles. Starts the same, of course, but then it starts changing, So the Second Symphony of Brahms has a nice example of an octacycle in it, in the first movement. And the great user of octacycles was Richard Wagner in his operas, but we'll come back to that a little bit later. There's another kind of octacycle. You see, the one that I just described has 4 different transitions going across the graph. So each of those transitions corresponds to a change from a major to a minor chord. But there's another kind of octacycle that just involves one switch between a major and minor chord, the one that involves F minor and F major here, and then the rest runs around the perimeter. So the F major and F minor, they're said to be parallel chords, parallel major and minor chords. So we say that this octacycle is a 1P octacycle. That's to say it's got one parallel shift in it, whereas the one that looks like the 4-cornered hat has got 4 crossovers, so we call it a 4P octacycle. So this is what a 1P octacycle sounds like. It's a different character to it. A little more progressive in some ways, the sense of going someplace. You can listen to it again to get the sense of it. So in fact, there are complete cycles of every even length, the maximum being the 24 cycle, which is called a Hamiltonian cycle, which runs all the way around the graph. So by use of the hexacycles, the octacycles, the decacycles, and so on, one can begin to analyze music in a variety of different ways. So here's some pictures of the cycles. The one on the left here at the top is the 3p hexacycle. You can see the 3 parallel crossings. The one next to it is then the 2p hexacycle, where there are 2 parallel crossings, and you have a sort of bow tie-like configuration. And then on the bottom left, we have the octacycle with 4 crossings. And then next to it, we have the other kind of octacycle with 1 crossing. So one can summarize these results in a couple of propositions. I want to concentrate on the proposition 2 for a moment. So it turns out that associated with every Levi graph, there's a configuration. So by configuration, I mean a collection of lines and points in the Euclidean plane with the property that a certain number of points lies on each line and a certain number of lines goes through each point. And what we're dealing with here in the Levi graph is a 12-3. That's to say we have 12 white vertices, 12 black vertices, and 3 black vertices are connected to each white vertex, and 3 white vertices are connected to each black vertex. And then the vertices correspond to major and minor chords, as we've discussed. But it turns out that there's a configuration, that's to say a collection of lines and points. You can draw it exactly in the Euclidean plane that has these properties. Now, in the 19th century, mathematicians were very interested in configurations. In fact, there was a point in his writings when Hilbert says that there was a point in the 19th century when the theory of configurations was regarded as the most important branch of mathematics. And it's not clear that that was really true, but certainly for somebody like Hilbert to make such a remark indicates that there was a lot of activity in that direction. So there was a mathematician called Dabrowski von Sternak who, in a couple of papers, started systematically investigating the different types of configurations. So for 7 threes, there is no representation on the Euclidean plane, but nevertheless there is a combinatorial configuration of 7 lines and 7 points, where 3 lines meet each point and 3 points lie on each line. And some of you will know it by the name of the Fano configuration, or the Fano plane, as it's called. And then there's an 8-3 as well. So this is 8 lines and 8 points, with 3 lines meeting each point and 3 points on each line. This was discovered by Mobius, so it's called the Mobius configuration. But curiously enough, it doesn't exist in the real plane. It only exists in the complex plane, a complex projective space of 2 dimensions. But the Mobius configuration is of great interest. When you get to configurations with 9 points and 9 lines, well, then there's the well-known Pappus configuration, which people learn in elementary geometry. But it turns out there are 2 others. So there are altogether 3 different 9-3s. And when it comes to the 10-3s, the situation is more exotic. There's one famous 10-3, which is called the Desargues 10-3. So this is just essentially Desargues' theorem in projective geometry, which involves 10 lines and 10 points. But there are 9 others, and so 9 of the 10-3s can be drawn in the Euclidean plane, but 1 of them can't. There's one that only exists combinatorially, but doesn't admit any representation in either real or complex space. Well, Dabrowski von Sternak started classifying the 11-3s and the 12-3s, and of the 12-3s, he discovered 228 of them. So they're labeled with a D number, so D1, D2, and so on. So there are 228 12 threes, or at least that's what Dublevsky von Sternach thought. It turned out that there was a mistake in his paper, and this wasn't discovered until 1990, and it caused great excitement amongst the combinatorialists when another 12-3 was discovered. So it's known now that there are 229 12-3s. And our tonnetz, as we discovered, turns out to be the 222 of Dublevsky von Sternach. So one can draw it, in other words, and there's a picture of it. And here's a picture of the tonnetz now drawn as a piece of Euclidean geometry. And you'll see that the major chords are represented by points in this figure, and the minor chords are represented by lines. And so, for example, you'll see this vertex down here is A flat major, and the vertex up here is C major, and then we have E flat major along it. And all three of these chords intersect with C minor. In other words, it's possible to get from C minor to A flat major to E flat major and to C major. And that's the tonnetz connection that we discussed earlier. And similarly, you can work through all of the other chords, and you can see they form this rather beautiful array in real Euclidean geometry on the plane. So that comes as a kind of a complete surprise. So, yeah, you can analyze the geometry in more detail. So you can see some of the things that we were discussing earlier. So, for example, the 3p hexacycles are the large triangles. So this triangle starting at A flat major going up to C major is a large triangle. And inscribed within it, there's another triangle here. And inscribed with that, there's another triangle. And then inscribed with that, there's finally a fourth triangle. And then if you extend the vertices of that fourth triangle, they go back and intersect the vertices of the original triangle that we started with. So in fact, we have a set of 4 triangles, each of which is inscribed in the next one. They're all sort of nested inside one another. And those are the 4 hexacycles that we discussed at the beginning, the 4 of the 3p hexacycles. So. And there are also 12 more smaller triangles, which are the 2p hexacycles. So in other words, one starts off with musical relations, then you transfer those to graph-theoretic relations, but finally we get a visual representation in Euclidean geometry. So, Dublevsky von Sternach was a contemporary of Hugo Riemann. Imagine them meeting, in a coffee shop by accident one day and having a discussion, what it would have been like. Well, I want to sort of shift gears slightly. The question is, how do you deal with more exotic chords? Here, many of you will know this snip of music. This is from Tristan and Isolde, the opera, right at the beginning. So the question is, how do you describe those 2 big chords, the first chord that it lands on and then the chord that it concludes on? So they have names. The first chord, well, these days we call it the Tristan chord. But this Tristan chord has a history. Wagner didn't discover it. He made it famous through his opera because the opera uses it over and over and over again. But the Tristan chord, it can actually be found in a string quartet of Mozart, believe it or not. But it's used very prominently in Chopin's music. And I'll give you an example. I'm sure many of you will know Chopin's Ballade in G minor. And the Tristan chord appears very prominently at the sort of first big climax of the ballade. And there's a huge arpeggio in the left hand where he plays 4 notes like that. That's the Tristan chord. But listen to the way that Chopin does it. You hear it in the left hand, the chord. I'll play it one more time because it goes by so quickly. So there, he uses Wagner's chord. In fact, it's identically Wagner's chord. It's not merely a transposition or a rearrangement of it. It's the same notes in the same part of the keyboard, note by note. This was 20 years or so before Wagner's opera, yes. So Chopin, maybe 25 years. So Chopin was well ahead of Wagner. And Chopin used these chords in many different occasions. I'll give you another example of Chopin's use. You see, he resolves the chord differently from Wagner. Wagner resolves the Tristan chord to an E major seventh chord, whereas Chopin resolves it to a B flat major seventh chord. And Chopin, it wasn't a one-off idea. Chopin seemed to love this resolution. So there's another one of his famous pieces, his scherzo in B minor, which is often used in concert recitals, and because it has a startling opening. But the startling opening is a version, of the Tristan chord, and then it resolves in just the same way as it does in the ballade. So another example of the use of this chord is in Tchaikovsky. So this comes later in the century. So Tchaikovsky was, his big symphonies came a little bit after Wagner's operas. So Tchaikovsky studied Wagner's operas. He got a hold of the piano score of Parsifal and was studying it intensely when he wrote his last symphony. So you see, so that's the opening of the last movement of the Sixth Symphony. And the first chord that you hear there is a version of the Tristan chord, and he resolves it to yet another chord. I'll play it again. That's the chord. And that's the resolution. I'll give you another example. This one comes from Wagner. This is from the opera Parsifal. So in this scene, this is in the Act 3, and at the opening of Act 3, Parsifal, after slaying the evil sorcerer Klingsor, goes on a long journey and then makes his way back to the land of the Holy Grail. And he's captured the sacred spear and he's bringing it back to the Knights of the Holy Grail. But when he returns, nobody recognizes him, and he's dressed in black armor and he's standing there. And one of the knights looks at him and is puzzled and wonders who it is. And he says, "You are not a member of the Brotherhood." So but he says this to this same chord. I just pressed the wrong button. That's Tchaikovsky again. And now you'll hear Wagner's use of Tchaikovsky's chord, the Knight. That chord. You're not one of the brothers, he's saying. So I'll play that again. So what's going on here is that you hear a kind of a fanfare, which is a sort of muted version of the Parsifal theme, and then you hear this version of the Tristan chord in Tchaikovsky's form, and then you have a series of descending Tristan-like chords, which reflect the knight's puzzlement as to who this intruder is. Play it again. So this is a picture of the score of the bit of Parsifal we were just listening to. You see the timpani playing at the beginning, and there is the brass playing this minor fanfare using a Tristan chord. So that's a fanfare based on a Tristan chord. And then it jumps up to a high note, and that high note is a chord which is identical to the form of the chord used by Tchaikovsky at the beginning of the fourth movement of his Sixth Symphony, and also used by Chopin at the very beginning of his scherzo. So this chord attracted a lot of attention. And then this is where Gornemans comes in and is puzzled about who it is. And then very softly you hear a sequence of these minor sixth chords reflecting Gornemans' bewilderment. So this leaves us with the question of how do you describe Tristan chords and these more exotic harmonies of late 19th century. These musical interludes are sort of designed to show that the problem isn't over once you've sorted out major and minor chords. There's more work to be done. So how do we tackle these? So what we did was to look at another construction. So we started over looking at the tonnetz, and we said, well, what happens if instead of just changing one note on each major chord, you change exactly two notes? So you have to keep one and change two fixed. Well, then it turns out you also get a 3-to-3 map between the major and minor chords. But this map, when you draw the Levi graph of it, sort of bifurcates into two different components. So you have two components, each of which has 12 vertices. And it's not strictly speaking a Levi graph because it admits tetracycles. You can see these cycles of just breadth 4. And you might think, well, it's an isometrical kind of figure, so what could this possibly represent? But it turns out that if you unfold it, it forms a perfect tessellation of the plane. So if this black vertex, which connects to the white vertex down here, if you put it next to another dodecagon and let it connect over to the next dodecagon, then you get a tessellation of the plane. I worked this out for myself, and then I was astonished to discover that this was known to Kepler. It was one of Kepler's tessellations. It's a one-off, one-of-a-kind, and this is what it looks like. So there's another tonnetz for you, based on Kepler's famous, it's in one of his notebooks, one of the famous tessellations of the plane composed out of dodecagons, squares, and hexagons. And so you can set these pieces of this tonnetz to music. So here, I'll play this particular hexagon that we have right here, starting in C major, going around in a circle. So we set it to music, and we put it into brass. So we call this, these tessellations, there are 11 of them. They're called the Archimedean tessellations, and this is the one that's due to Kepler. This is our fanfare. So that's based on the 6 chords of this this particular hexagon there. I'll play it one more time so you can just mark the chords we're at as we go along. So that's C major. It goes by rather quickly. First chord, second chord, third chord, fourth chord, fifth chord, sixth chord, and then back to the beginning. So it starts and ends on the C major. So after we looked at this, we had the idea that maybe one could extend the tonnetz in an interesting way by looking at chords based on 4 notes and then requiring that 2 of the notes change, but you always hold one of the notes fixed, and the note that you hold fixed is the dissonant note. And so more precisely, if you consider the so-called Tristan genus, this consists of dominant 7th chords and minor 6th chords. The minor 6th chords are the so-called Tristan chords. And the dominant 7th chord is a familiar chord from classical harmony. And if you take the dominant 7th, it has one dissonant note in it. So if you have a C major dominant 7th, or C7 as it's denoted here on the graph, then that's got C, E, G, and then B flat in it. So B flat is the dissonant chord. And then you can resolve that to a chord that is a minor 6th chord, but then contains the same dissonant note at the top. It preserves the dissonant note. And you find that these dominant 7ths resolve to 3 different kinds of minor 6th, and each minor 6th then resolves into 3 different dominant 7ths. So you get another tonnetz. And in fact, the graph looks very similar to the Eulerian tonnetz that we started off with. But then we have a kind of a surprise, because it turns out this is not the Eulerian tonnetz. It's not isomorphic to it in any sense, but it's another 12-3. And so there's the general theorem that if you have a 12-3, then it must be one of the 229 of Diblewski von Sternach. So the question is, which one is it? Well, it's known to the graph theorists that the 12-3s of the 229, there are exactly 4 of them that are completely symmetric, in the sense that the group acts transitively on them, which means you can get from any chord to any other chord by suitable group actions. So it's got a rather large group. And the tonnetz is one of them. And this turns out to be another one of the homogeneous ones. So this turns out, we can go back to the proposition here, proposition 3. If you take the Tristan genus, which are the chords containing the dominant 7ths and the minor 6th, then you can fit it onto a 12-3 and form the Levi graph, which you just saw. And then that turns out to be another one of Diblewski von Sternach's configurations, and it turns out to be 228. So the very last one that he discovered, of course there's one more, but that came later. So this is the very last one. So it was a good thing that when we were looking for these things, we weren't going through Diblewski von Sternach's, paper one configuration at a time, because it would have taken a long time for us to reach this one. But we managed to get it. So so this is what Diblewski's 228 looks like. So this is the Tristan genus, and you can see that the actual configuration is in some respects a little bit simpler than that of the Eulerian tonnetz. And it comes as a surprise, but it sort of indicates how natural, in some respects, these harmonies are that you have when you mix the dominant 7ths and the minor 6th chords. So I wanted to mention another example. So here I've brought out a little bit of the score of Götterdämmerung. So this is Wagner's climax of the ring cycle, and it may not be obvious by inspection of the score, but he has a more or less complete octacycle of the Diblewski 228 configuration here, starting at this A major. So what's going on here is that, I don't know if you're familiar with the opera or not, but if you are, there's a scene just towards the end when the hero Siegfried has been killed, and they're preparing a funeral pile for him. And then Brünnhilde, the Valkyrie, is there, and she orders the vassals to pile the logs up higher and higher because she wants to set this huge fire. And this is the scene when she's ordering them to build the fire. And what happens next, which I won't play, is that she jumps into the fire herself, and then the fire consumes the whole of Valhalla, and then that's the end of the opera and the end of the ring cycle. But this occurs, about 5 or 10 minutes before the end of the opera. But what happens is you'll hear the progression of an octacycle, and I can even show you the octacycle on the graph. So it starts at the A dominant 7th chord, which is this vertex at the bottom. And then it moves to this B flat minor 6th chord, which is this line. And then it goes up to the C dominant 7th chord, which is this vertex here. And then it moves across the line at the top, which is this C sharp minor 6th chord. And then it reaches the D sharp 7th chord, and then finally an E minor chord, and then it moves to F sharp major. And at that point, Wagner could have brought it around, but then he'd just have to play the whole opera all over again. So he cuts it off at some point, just in the way that Beethoven did. So basically, Wagner goes all the way around to the bottom, and then he nearly makes it to the next chord, and then stops it there, shifts gears, and moves on to something else. So there's a kind of a climax once you reach the bottom. But you can hear, I'll play the musical excerpt now, and you can hear the transition of the chords quite clearly. I'll show you on the mouse as we go along.
Excuse me, just 5 more minutes, please.
That's fine, I'm nearly finished. This is the A 7th chord. Now that's the B flat minor 6th chord. And the C 7th chord here. This is Brünnhilde, the Valkyrie. C sharp minor 6th. D sharp 7th chord here. This is the E minor 6th chord. Now she's preparing for the climax. And this is the F sharp that she finally reaches. So there's an example of Wagner's use of octacycles. And I read a biography of Wagner once, Wagner's autobiographic, and he, Wagner, he was very full of himself and so on and so forth, but he does confess one weakness in his autobiography, and he says that he was never any good at mathematics, which I thought it was curious. Of course, it's not unusual for artists, to make such claims, but nonetheless, one can appreciate that there is a kind of almost strange affinity, between mathematics and music, and it even kind of reaches up into the higher abstractions of projective geometry, into constructions, that the 19th century musicians wouldn't even have dreamed of. In any case, thank you very much for your attention.
Thank you very much. We have the first question.
All your examples were referring to 19th century music. How about the earlier things, Baroque, Bach, Vivaldi?
Well, that's a good question. I mean, the musicologists have investigated this question extensively, and the answer is that that yes, you find throughout the 18th and the 19th century, you find examples, but they come more sparse. If you move back into the 17th century, then you don't tend to see them so much. And I guess it was really around the time of Bach, and his immediate predecessors, such as Buxtehude, when you begin to see the more sophisticated use of harmonies and changes of key and modulation within pieces, that you then begin to see tonnetz-like constructions entering into the music. So the way that the musicologists say it is that the tonnetz seems to be an artifact of what is called the common practice period. So the common practice period, that means from late 17th century right up to around 1900, at which point, one has another kind of phase transition in the character of music. Of course, it continues in modern day music, in popular music, and in film music particularly, where film music is drenched with the tonnetz. You hear this sort of idea being used all the time.
I have a feeling that none of those graphs represents really the relation between the musical relation between those chords. Just first remark that I strongly protest against treating those three minor chords assigned to one major chord. Because if you take, for instance, C major, and those three minor chords are A minor, which is really very, very close to C major. It is almost the same, whereas the remaining two are much more far away, namely C minor and E minor.
Correct.
They are very distant. So this is one thing. Another problem is that the fundamental structure is based on those triads, which are three adjacent on this 12 how you call it, excuse me, I don't, yeah. So starting from C major, the fundamental chords are F major and G major. In jazz music, mostly with seventh, yeah? And this is the fundamental structure, I believe, based on those triads, which practically are absent. These triads are absent in those.
Yes, well, that's a useful observation. And of course, the musicologists are well aware of this issue, and they talk about it all the time. And this controversy is right at the heart of the issue of what is music. And the musicologists are divided on the point, and many would express exactly the same opinion that you have voiced. So you're in good company, that's for sure. But on the other hand, the other side of the argument, they say, well, in reality, it's as though there are two different systems of music being employed simultaneously from the 19th century on. And you see this in all of the main 19th century composers, that to be sure, as part of the skeleton of their work will involve more or less conventional harmonies with standard resolutions. So when Chopin wants to end a piece, he plays a dominant seventh G major chord, and then he resolves to C major, and there's no other way to end it. But when he wants to begin the piece, he doesn't necessarily do it that way. He does it a different way, and you wonder, well, where does that come from? And that's what makes Chopin and many other composers of that period original, because they have kind of surprising twists in their harmony that can't be explained using kind of classical harmonic theory, but they do fit in rather nicely with the tonnetz. So it's not that you must use this system or you must use that system, and it's certainly not that you would use the tonnetz exclusively, but rather what the 19th century composers were doing, because after all, they were brought up on classical harmony, and that's what they studied themselves. They would use that as the framework for their pieces, but then they would intrude extra layers of harmonic structure that they thought about intuitively. They would intrude these extra layers of harmonic structure that didn't seem to conform to the familiar patterns. An early but a very important example of this are the works of Schubert. So Schubert wanders all over the place in the keys in his compositions, and you wouldn't be able to pick up any theory of classical music textbook and explain how Schubert goes from here to here, but it fits in rather nicely with a kind of a tonnetz theory. So that's really one shouldn't view the theories as being in opposition to one another, but rather that the tonnetz adds an extra depth of explanation for certain types of chord transitions that would seem to be impossible, within the classical framework.
Okay, thank you very much. Are there any questions from the Zoom viewers? If not, then thank you very much. Let's thank our visitors again.